So this is Kirby Shedden from CSCAR, and this will be approximately a 2-hour-long workshop / discussion on data methodology and COVID. So this is the first in a series of what we hope will be a series of workshops to be run over the course of the next couple of months on a variety of topics that are somewhat inspired by the COVID situation and by the fact that many of us are stuck at home and wishing to train up and learn new things. But not really narrowly focusing on COVID per se, but rather on techniques and data that are relevant for public health more broadly, population health more broadly, that may have some implications for understanding what's going on with COVID, but also have implications for lots of other things in public health as well. So the first workshop, the one we're going to have today, is on statistical analysis of mortality data. So these will all be more on the technical side. I'm a statistician, not a medical researcher or public health researcher. So this is more on the technical side, meaning methodology, issues with careful analysis and interpretation of data. We can get into software and algorithms if people are interested. We can actually do whatever people want. These are for everyone's benefit. So I'm happy to get comments and feedback from people as we go through this, suggestions about possible topics for future workshops. I have a few ideas for things that we could do next. But I'm not wedded to any one particular thing. So I'm very happy to get suggestions from anyone who would be wanting to do so. We can have more of like a hacking type session if people want. One of the key things here is that all of the data and tools that we use throughout this series will be open source, open data, open tools. So we could, today it'll be more of a lecture, but in the future we could go to more of a hackathon type format if that's what people are interested in. So basically what I'm hoping to do here is to give like a short primer, because you can only do so much in 2 hours, about some tools that I use and find to be pretty effective and useful. And that will inspire people to go off and play around basically, because I'm going to give you data and tools. You have these notebooks that we're going to walk through today, and you can view this just like as a starting point. So you can take these notebooks and take the data, and there's lots and lots of things that you can do going way beyond what I have done and what I'll be able to talk about today. And I'll give some hints as we go along as to directions that someone could expand on. So just view this as a germ of an idea that any one of you could develop on your own. And if we want to have a future session be centered around people presenting what they've done, following up on what I present, that would be great. I'd be very happy if other people take things far enough and they feel comfortable sharing what they've done, and then I get to watch. That's perfectly fine with me. So, and like I said, these will be occasional. There's no fixed date for the next one, but I'm going to try to get something together every 2 or 3 weeks, and I've got 4 or 5 of these in mind. Again, suggestions are welcome. So with that said, I'm going to flip over to screen share. Now this, of course, is a Zoom thing, so I can't see any of you. I know there's about 20 people out there, at least there seem to be about 20 people out there. And please do, oh, there's 40 now, so things are growing. So if you have questions, I think you can unmute yourself and just shout out. Even with 40, I think that's totally fine. I'm actually not 100% sure because I don't normally use Zoom meetings or Zoom webinar or whatever this is. Because unfortunately, once I switch over to my screen share, I can't check back the chat list anymore. So if you have questions, I think you have to do something like either speak up or raise your hand, and hopefully that will show up over the top of my slides. This discussion that we're about to start on has roughly 3 parts. So I'm going to spend maybe 15 minutes talking about the data, and then 40-ish minutes talking about each of 2 different analysis notebooks. And so I will break out of the browser twice during the workshop in order to take questions. So at least I'll be able you'll be able to get my attention then. Okay, you should have gotten an email. Let me see here. I need to web URL. Okay, hold on a sec. This might be a little bit painful. Maybe I should just do this from the PDF. I think I'll just use the PDF. That's easier. I thought I'd be able to open my browser, but it doesn't seem that I can do that on Zoom. So give me a sec here. Document. Oh shoot, I didn't even download the right one. Nuts. Okay, hold on a sec. Bear with me. I just got to download something real quick. Oh, nuts, I don't have a PDF version of that. Okay, I'll just talk about the first thing. The first thing, you don't need to see it. So let me open up the second thing, just so you have something to look at while I talk here for a minute. So is it here? I hope. Here we go. I'll tell you what I'm doing here in just a sec. Just let me get it done. I can't talk and do stuff at the same time. Okay, so you should be seeing a PDF file that says mort_glm. That's just the file name. And unless someone speaks up or texts me or chats me, I'm going to assume that you can all see that. Now, this isn't the first thing I want to talk about. I didn't have the first thing downloaded because I thought I would be able to share my browser with you. So sorry about that. All right, let me just zoom out a little bit. Can see the PDF. Great, thank you. So this workshop is going to be about mortality patterns in the US over a roughly 18-year time span. So we're taking data, official US government data on mortality in the United States from, I think, 2007 up to 2018. So 2018 is the most recent year in which these data are available. So that we're not actually going to get into COVID, of course, just because of data availability. And 2007, there is mortality data going back to the 1970s in roughly the same format, but they changed some of the definitions of how variables are defined. So it's a little bit trickier to integrate data from post-2007 and pre-2007. So I'm just gonna keep it a little bit simple. We'll be complex in some ways, but in this way we'll be simple and we'll focus on data. Yes, I will tell you where to get the the PDF file in just a sec. I'm going to keep it simple and work with the data from 2007 to the present. So the files that I'm showing you now are all on GitHub. And if you're registered for the workshop, you should have gotten an email this morning with the link to all of this stuff. And if you didn't, I'll read it out right now. So it's at GitHub and under my GitHub account. So it's github.com/kshedden, KSHEDDEN. And then /workshops, so kshedden workshops. And then you go into the workshops directory of my GitHub account, and there's about 8 or 10 workshops in there, and one of them is called Mortality. So kshedden kshedden workshops Mortality. And then under Mortality, there's a couple of folders. One's called Python and one's called Notebooks. And in the notebooks folder there is the PDF that I'm discussing right now. I was actually planning on there's the exact same file is present there in 2 different formats. One is IPYNB, which is the IPython notebook format or Jupyter notebook format, and one is PDF. It's exactly the same. It's just because of Zoom, I was going to share my browser window with you, but it looks like it's not that easy to do that. So I'm going to lecture off of the PDFs. It's exactly the same except for like formatting, fonts, and so on. But if you're following along, you might be better off opening up that mort_glm.ipynb notebook. And I'll say a little bit more about notebooks in a minute. But I would open up the notebook. It just renders a little bit more nicely in the browser, but it's exactly the same information. So if people are struggling, if everyone's struggling to find this information, then someone stop me. But you should have gotten the link this morning in an email. Yeah, there. Thanks, Jing. Now, this is a Python-based workshop. I guess I didn't mention that, although it's more about methodology and less about software, but we have to have some software, and so it's going to be Python-based. We'll see if a future workshop, I might just mix it up a little bit, but probably Python works for a lot of people, if not everyone. And I'm using Jupyter Notebooks because people seem to like Jupyter Notebooks. So if you're at all familiar with the sort of Python ecosystem for data analysis, you know that Jupyter is the GUI system that a lot of people are using now to do interactive analysis and coding in Python. So you should be able to download these Jupyter Notebooks. You can just view them for now during the lecture, but afterward, if you want to pick up where I left off, you should be able to download these notebooks and play with them, extend them, try things different from what I did to see what happens. So they're basically documents that you can, they're like living documents that you can work with on your own system. They're actually, I don't actually use Jupyter myself. So these, just to make things a little more complicated, these Jupyter notebooks were derived from Python scripts. And those Python scripts are in another directory of that GitHub site, which is the Python directory as opposed to the notebooks directory. And then I use this tool called JupyText to convert the Python scripts into these Jupyter notebooks and PDF files. It's all the same information. Whether it's the Python script or the Jupyter notebook or the PDF file, it's all the same information. It's just in 3 different formats. So hopefully that's not too confusing. But for most of you, you probably, if you actually want to play with the data, you'd want to use the Jupyter notebook. That's the easiest way to get going. This isn't really an intro Python workshop, so I'm assuming that people who want to actually work with the code are able to do that. And it's perfectly fine if you want to just focus more on the methodology and the conceptual layer of this. Then I'm going to mostly be talking about the concepts and the modeling techniques and the statistical issues, and not so much on the code. I'm not going to really go line by line through the code. But if you want to really drill down and do some of this stuff yourself, eventually you do have to learn more about the code. Again, it's Python. Python is just a programming language, so it's Python with the usual data science stack within Python. So we use pandas for data management, NumPy for numerical analysis, stats models for statistical modeling, and matplotlib for graphics, for visualization and graphics. So that's the usual set of tools that people use when doing statistical data analysis in Python. I think the last thing I have to say by way of introduction is that I have 3 scripts. Again, all 3 are in the .py format, Python scripts, as well as in IPython notebook format. And the first one's called Vital Stats Prep. And that's the script, that's kind of the boring, tedious script that pulls the data off the web and massages it into the right form. So that's important, but not especially interesting to lecture on. So I'll spend less time talking about that. And I don't actually have a PDF version of the Vital Stats Prep script. I have only the Python and notebook formats. And then the 2 more interesting ones that get into analysis are the GLM, generalized linear modeling, GLM, mortality using GLM, and then PCA, principal component, or generalized principal component is what we'll get to later. So this data is a little bit tedious to work with. It's like I said, I want all of these workshops to be focused on open source data, openly available data. So no one has to ask anyone's permission to download this data. It's right there on the open internet. But there's a bunch of files, and they're kind of in a convoluted format, and you have to read the data dictionaries quite carefully to get the information out that at least I wanted for this analysis. So that's basically what the Vital Stats Prep script does. I'm definitely not going to go through it line by line. I can't even pull it up now, which is maybe a good thing, because it would just send us down a rabbit hole to get into that. But you know, that's a skill that many of us need. Rather than downloading 20 files manually and renaming them and risking like scrambling things up, writing a script is almost always the better way to go. So that script is a bunch of data munging. The Vital Stats Prep.py is a bunch of data munging that produces the data files that we're going to use for the analysis here. Just very high level, so you understand what these data are. So there's a couple of different ways in which the CDC, this is the US CDC, where this is all going to be US data for today. In future workshops, we can definitely look at some international data, but this is US data. And the CDC releases mortality data in various formats and fashions. They actually record every death, every individual death. So at some level, the raw data are totally disaggregated, individual human deaths. And they get quite a amount of information about each death, but they don't publish it in a way that would make it too easy to de-identify who is whom, although it's not exactly clear how much privacy you have when you're dead. But for whatever reason, the open downloadable data is somewhat aggregated, which is fine for us. We actually want to work for this analysis today with very aggregated data. So you can either get it at fairly fine temporal resolution, but no spatial resolution, or you can get it at fairly fine spatial resolution, but no temporal resolution. But you can't get it at both high temporal and high spatial resolution at the same time, because that would make it relatively easy to find people you knew where they live. If you knew where someone lived and when they died, you'd be able to find them. I think the sensitivity is this also has information about cause of death and so on. I guess maybe people sometimes don't want their cause of death to be totally out there on the internet. So anyway, for the sake of focusing in today, we're just going to look at the data that's more temporally resolved, but not spatially resolved at all. So there's not going to be any sub-US spatial story here. We just, everything north, south, east, west, it's all lumped into one big bucket. And in order to get more temporal resolution, we have to sacrifice the spatial resolution. Now, of course, if you're a legitimate researcher and make a request to the CDC, you can get disaggregated data, but then you have to jump through a bunch of hoops, and that's not you know, good for like a workshop, a training workshop. We can't all get that level of permission just when we're learning how to do stuff. So I opted for the more temporally resolved data here. It's actually individual data that we get. It's just that the location is masked or gone actually. And then I wrote the script that aggregates down those individual death records to totals. And actually right here on the bottom of this page 1 is the top like 5 rows of the data. There's 5,184 rows of data, and these are the first 5 rows of data, and all columns. So there's not that many columns here. This is not a terribly complex data set in some ways once you pack it down, but there's actually a lot of subtlety to the analysis, as I hope you'll see. So again, the data starts in 2007. We have data per month within each year from 2007 to 2018. And we have the number of people who died in the United States in a given age group. So 1,087 girls under the age of 5 died in January of 2007. And we'll be interested in rates, so we need to know the total population. So that's the other thing that that Vital Stats Prep script does that maybe I didn't mention earlier, is that it goes to the Census Bureau's website and downloads the census data, so we understand like what the denominator should be for a death rate. 10 million or so. Can I show the data on the screen? I mean, the data is 5,000 rows long. I actually can do very little on my screen, sorry, because I'm working off of a PDF here. So I just have the first 5 rows of data. If you mean the location of the data, or I'm not sure if you mean the location of the data or the data itself, but the location of the data is embedded in that Vital Stats Prep script. So if you are curious about where the data came from, exactly where on the internet the data came from, just open up the Vital Stats Prep script, and the URLs and FTP addresses where the data comes from are all there. So if you wanted to run all this yourself, thanks, James. I'm just going to leave it like this for now, and then when we switch from this workshop from this demo to the next, I might try to do it via the browser. This seems to be working okay. I'm fine working off PDF. So if you wanted to run this analysis yourself, you'd have to get the 3 scripts. You'd have to run the Vital Stat script because you don't have the data. You just have the scripts. And then the Vital Stat script will pull all the data down. It takes like 20-30 minutes to run that Vital Stat script. There's a fair amount of processing that takes place. And then you'll have the data on your local system. And then you can run these 2 analysis notebooks against that data. You will have to tweak. There's a few file system paths in these notebooks that you'll have to tweak. They're currently set to point to address to directory paths on my system, which obviously won't work for you, but it should be obvious. It's just I think one path at the beginning of each of the 3 notebooks you'll have to customize for your system. So you can study I don't want to go into all the details now, but you can study the Vital Stats Prep script if you're interested in the details of how I got the data and what I did to it. But I think at a high level, to understand the concept of the analysis, all you need to know is that the bottom of this page 1 we're looking at here shows the top 5 rows of the data set. So it's not very wide. There's not a lot of covariate information. Probably a more, anyone worth their salt would have disaggregated by ethnicity. So they have race and ethnicity data in the file. But it gets complicated because there's so many ethnic groups and racial groups and missing values and so on. So I decided for the sake of this workshop not to disaggregate by ethnicity. And of course, we can't disaggregate by geography either. But of course, a real deep analysis of this type of phenomenon would do that. So that's one of the directions that you could pursue on your own. And if I didn't make it clear, like, why do we care? Why do we want this data? Why do we want to analyze this data? Well, there's a bunch of reasons why. There's great interest in mortality trends just on their own terms. Mortality has been trending down more or less from the dawn of civilization, I guess, with a few spots in between where we had plagues and so on. But certainly since World War II, mortality has trended down pretty much monotonically. And there was some big news in the past few years before COVID about mortality gains plateauing, and that possibly being related to either the opioid epidemic or to the after effects of the Great Recession. And now we've got this other huge thing going on, which is going to profoundly impact mortality, at least for a short period of time. So in order to understand like deviations from what you might consider normal mortality, I hate to say normal mortality, but if you want to consider anomalies or deviations or unique events, you have to understand the background patterns against which those unique events are placed. So that's really the best way to think about what we're doing here is we're going to model the mortality data in order to understand what are the seasonal effects, what are the age group differences, what are the sex effects, in order to establish what was sort of the normal trend line from 2007 up through 2018. And then so people are already starting to make some rough guesstimates about how COVID will superimpose upon this data, but I certainly can't do that now because that's a whole other issue. Like obviously there's not accurate COVID data yet, and even the underlying mortality data is not up to date to the COVID era yet. So in a couple of years, people will be able to simply extend the analysis we're doing here and see what COVID did. But for the time being, that would require, doing anything with COVID requires a lot more work. It requires taking early versions of data with all kinds of anomalies in them and somehow harmonizing it with this more solid data. So I'm not going in that direction today. So again, this workshop has COVID in the title, but it's kind of in the background for this workshop. And then as I said, future workshops in this series, I actually have some more recent data that actually is COVID specific, and we can look at that. So this is really about understanding trends in mortality, and it's all cause mortality. You can look at mortality due to different causes like injuries versus violence versus disease, but that gets complicated, of course, because you have to deal with all the irregularities with cause of death reporting on death certificates and so on. So that's really important and interesting, but there's a lot that can be done looking at all-cause mortality, and then you don't have to worry about any of those vagaries. And the US and most advanced countries are very good at tracking deaths. So essentially we have a census of deaths here. This is a complete data set of all deaths. It's not a random sample or a subset or a convenient sample or anything like that. It's an honest census of all deaths in the US. So it's quite complete. Okay, so so what I did here, now we're into the first of the two analysis scripts. So what I want to demonstrate today with these data is two different ways to achieve the goal that I just laid out for us. So the goal would be to understand patterns and trends in mortality data over a 18-year time span. That's not 18 years, what is it? It's 12 years? Yeah, I think 12 years, 2007 to 2018. So 11 or 12 years. I said 18 because there's 18 age bands. I'll talk about that in a minute. We got the 18 and the 12 mixed up. But so what are the trends in these data? And so trends is kind of a vague term, but we can get at trends via regression analysis. We can get at trends via something like principal component analysis. So I'm a statistician, so at the end of the day, these are all statistical techniques. And sometimes people say that like 80% of applied statistics is regression. I think that's probably true. And the other 20% is largely multivariate analysis, of which principal component analysis is the core tool. So we're using what most people would consider to be the most obvious tools here. You could use some fancy exotic techniques to get a handle on these same questions, but I'm not doing that. Instead, I'm just going to the first thing that I think any reasonable statistician would consider as in terms of the right tool for the job here, in terms of understanding the mortality trends in these data. So this first, the GLM is mortality generalized linear model. So generalized linear modeling, this isn't the time or place to go through the whole history and infrastructure around generalized linear modeling. GLM, one of the big breakthroughs of statistics in the dates to the 1970s, although builds on antecedents going back much further. So it is probably should be the workhorse for a lot of data analysis, and not terribly difficult to master. Like it's a lot easier to master GLM, I think, than it is to master like mixed modeling, say. So it's an advanced undergrad, beginning, graduate topic. You wouldn't usually get to it in your first statistics class, but it's not like a super advanced technique. You don't have to understand a lot of, say, theory to make good use of GLM. So GLM is actually very flexible. It encompasses a lot of things that people rarely consider, like gamma regression and Tweedy regression and so on. So I won't have the time or take the time today to get into all of that. We'll be talking today about Poisson, largely about Poisson and quasi-Poisson GLM, which is very powerful, very widely used in epidemiology and demography, but many people also don't know that much about it. So this will give us a chance to see how these techniques work in a real case study type situation. Other GLMs that you probably have heard of and used would, of course, be logistic regression, and even linear regression is a GLM of a type, but a lot of times people don't think of it as such. But to me, Poisson regression is like really useful, and the prototypical GLM, and you can really get a lot out of data like this from working with Poisson regression. It's actually, the Poisson is sort of a misnomer almost, because Poisson makes people think of Poisson distributions and so on, and there is a bit of a role for Poisson distributions, but actually Poisson regression, and that's why sometimes people call it quasi-Poisson regression, is way more broadly applicable than you might think if you're thinking narrowly about Poisson distributions. I mean, there's no reason why deaths like pooled across all space and time should be Poissonian in any way, but yet we can still get a lot of information out of the data by analyzing it using Poisson regression. By the way, feel free to send questions by that chat tool. I was seeing some questions show up earlier, and I'm happy to I'll keep an eye on the screen and try to respond to questions as they arise. So we'll be using Poisson and quasi-Poisson regression here. Those are GLMs. So the key thing I want to focus on here at the beginning of the discussion, which is really important, is what is the consequence of doing a Poisson regression, because the Poisson regression, you may have heard this term before, of a link function. The Poisson regression has a logarithm as its link function. So that has really profound implications for why Poisson regression yields informative results, but that have to be interpreted in a particular way compared to what you might get, say, from linear regression or logistic regression. So linear regression tends to be more additive. You can kind of trick it into being multiplicative, but let's not go there. That's a separate discussion. But normally when you do linear regression, you're imagining that the output of the system that you're studying is related to the inputs in an additive way. And when you're doing Poisson regression, or its cousins like negative binomial regression and Tweedy regression and so on, you're thinking that the output is related to the inputs in a multiplicative way. And it turns out that a lot of the time, a multiplicative structure is more interpretable, more natural for many sorts of real world phenomena than additive models are. So what do we mean by multiplicative? I'm going to switch the slide here. I've written a lot of words. I'm clearly not going to read all these words for you, but you can read them on your own if you like. What multiplicative means is that each factor in the model, each covariate in the model, operates by scaling or multiplying against the effects of all the other covariates. So I have an example here in this paragraph on the top of the slide that I just made up these numbers. But let's imagine that men have 5% greater risk of dying than women, and that deaths in January are 3% more than deaths in June. Then a multiplicative effect would mean that that men in January would have 1.05 times 1.03 times the risk of dying than a woman in June. So in other words, those two covariates, the time covariate and the sex covariate, combine multiplicatively to influence the response variable, which would be the death count for us. And that's really, really important. Actually has more profound implications than I think a lot of people realize. Again, in an additive model, you would be saying something like, there are 3,000 more deaths for men in, say, January than there are for women. That's an additive effect because you're counting the number of additional deaths. Whereas a multiplicative effect is more, you think about it in terms of a percentage. So it's saying that there's 5% more deaths. And the reason that multiplicative effects make a lot more sense in many situations is that, you know, you have different amounts of deaths at different seasons in first order and in different age groups, like far more deaths among older age groups than among younger age groups, of course. So at first order, you would think that it wouldn't be that there would be like 3,000 more 80-year-old men die than 80-year-old women die, and 3,000 more 30-year-old men die than 30-year-old women die. It wouldn't make sense for it to be the same additive amount. It would make a lot more sense for it to be a multiplicative difference, like a percentage change. So Poisson regression just naturally expresses the covariate effects in that multiplicative or percentage type way. It's actually a very simple idea. I don't mean to imply it's anything very deep, but a lot of people will just jump to linear regression, and for data like this, it's very strange. It would actually be very strange the more you think about it to think in terms of additive effects rather than multiplicative effects. Now, one thing that sometimes confuses people, and I don't want to dwell on this too much, but the log as a link function is not a data transformation. So when I say that the Poisson regression has a log link function, it's not the case that you just log the data and then use least squares on it. So transforming the data is not the same as having a link function. Transforming the data in many ways is more the old-fashioned way of modeling data multiplicatively before the GLM technology was fully developed in the 70s. In the 1970s and 80s, people would just log transform data. that's fine up to a point. It works when it works, and sometimes it doesn't work so well. But what we're going to do here is not that. So I don't even want to talk about that anymore. We're going to model the data with Poisson regression, and the log link function is expressing how the covariates relate to the fitted mean. It's not implying that we actually logarithmically transform the data. Okay, so I guess the other thing I want to say is that our goal here is to understand and not to predict per se. So we want to understand what this is all historical data. And like I said before, it's actually a census. So there's no need to predict something. We know exactly how many people of every possible type died at any given time in the past because the US CDC tracks that information. So the goal is to understand what are the underlying factors that may influence mortality, not to make predictions. This is not a forecasting exercise at the moment. Although some of these tools can be useful for forecasting, that's not our goal here. And we also want to be as robust as possible in the statistical sense. The word robust is a little bit problematic because it means different things to different people. But in the statistical sense, robustness means that our conclusions aren't hinging on fragile and hard to verify assumptions behind the methodology. And so one of the nice things about GLMs is that they have very nice robustness properties. They're actually applicable much more broadly than you might think. And this goes back to something I said earlier about the Poisson regression, not really being about the Poisson distribution. So you can, there's mathematical theory that shows that you can get very meaningful results out of Poisson regression, even if the data are not Poissonian. And we'll come back to this a little bit later. So it's not like any technique has infinite robustness. So it's not like this method will work for any conceivable data, but we can be precise, a little bit more precise later on. But this quasi-Poisson or Poisson regression that we're using here has the potential to give meaningful results in a very broad set of possible scenarios. It's not like what you might call a very parametric type of analysis that has very fragile assumptions that are hard to check and easy to violate. Okay, all that, we're half hour in now. Let's actually look at a model. So since I can't point on my screen here, I'm just gonna say cell 5. So hopefully you can see the cell numbers in these notebooks. So cell 5 is where we fit our first model. I'll need to go back and talk about this offset in a minute, but let me just continue. So this is how you fit a generalized linear model in Python using the stats models library. So maybe some of you have been to some of our CSCAR workshops on generalized linear modeling and have already seen this. I'm not going to focus on the syntax too much, except just to say that we have a formula that describes the regression structure, and we fit it using the GLM function and make sure we specify that we're using the Poisson family, although I'm actually going to interpret this in the quasi-Poisson framework. So we'll talk about that more in a minute. You create the model and then you fit it. So M1 is the first model and R1 are the results that you get from fitting that model. This, of course, can be done in R. It would be a nice exercise. People who like R, I like R, but I'm not using it here. People who like R could translate all this into R very easily. This is not in any way Python specific. And actually the formulas are very R-like formulas. This R formula syntax has kind of become universal across all statistical packages, extremely helpful. So the formula there, if you're not familiar with this type of formula, deaths tilde age group, sex, year, month. So this is an additive model. Actually, I should say it's a pure multiplicative model, not an additive model. It's a pure multiplicative model, which means you have age group effects, sex effects, year effects, and month effects that multiply together to produce the overall fitted expected mortality. Okay, and so very briefly, the age groups are, this is just the way the CDC does it. They have age bands. I think there's 18 of them. So it's 0 to 5, 5 to 10, 10 to 15, and so on. And then 85 and up. So there's one band at the end, which is bigger than the rest. So there's the age band. So we count the number of deaths per age band. This is biological sex. So we have females and males, years 2007 to 2018, and months, of course, January through December. The C just means we're treating year and month as categorical variables. And one could approach this in a different way using splines or other like smooth functions, but I'm not going to go that route right now. So here's a very basic generalized linear model, GLM, Poisson GLM. Now this model will already have 18 parameters. So you're used to regression perhaps, and just looking at the table of fitted parameter estimates, that's not going to get you very far with this data. It's going to be just a bunch of numbers that don't seem to mean anything. So what we want to do is we want to use visualization, not tables of output, to get a handle on what these models mean. And so we'll get to that in a minute. There'll be some slides, some graphs we can look at later. What I'm going to do first is I'm going to fit a series of models using different variations on modeling. And then we'll go to the graphics. So I'm going to fit different models, and I'm going to settle on a model that seems to fit the data reasonably well. And then we'll look at the graphs to further understand what we've learned. So this is a very basic model. This one in cell 5 is a very basic model. Oh, let me talk about the offset, sorry. So one more thing is we want to include population as an offset. So you may or may not be familiar with the notion of an offset in a GLM, Poisson GLM. An offset in a GLM is basically like it's a covariate. You can think of it a couple different ways, but one way to think about it is it's a covariate that's always included, but with a coefficient of 1. You don't estimate its coefficient from the data, you just fix its coefficient at 1. The upshot of that will be that we're always going to look at deaths relative to population. So if, again, say if males have a 5% greater risk of dying than females, it's actually much more than that, but let me say it's 5%, then that would be relative to whatever the population is. And so we have to have the population data for this to work out. So that's why I got the population data from the Census Bureau, and it's got to be log transformed for reasons that are relating to the way the link functions work together. So let's not go there now. It's just a mathematical thing. So in cell 4, I took the population data and log transformed it. In every single model from cell 5 down to the end, I'm always going to be including log population as an offset. So that is in order to make the effects relative to population. We don't care, like if the population jumps due to growth or immigration or whatever, of course, eventually the more people are going to die. Everyone dies eventually. So that's not what we want to focus on here. We want to focus on the death rate. But I don't want to actually take the death rate literally. I don't actually want, and this is usually the way that epidemiologists approach this type of data, epidemiologists and demographers. You don't want to just literally divide the number of deaths by the population. It sounds like a natural enough thing to do, but it actually creates a lot of statistical problems. That kind of proportion data is a little bit hard to analyze. So it's much nicer to analyze counts with a population offset. So analyze the numerator using the denominator as the offset, rather than literally dividing by the numerator, dividing the numerator by the denominator. That's okay, but for regression analysis, it's nicer to analyze the numerator as the dependent variable in a regression with the denominator as an offset rather than the ratios directly. At least that's my preference. Okay, so that's the model in cell 5. Now we don't get anything out of it. What we're going to do instead is we're going to compare models to each other statistically. Now there's a couple of reasons why one might doubt the model in cell 5. So it's actually an overly simplified model. There's no way that this model is the right model. One is that it's purely multiplicative, like I said before. And 2 is that it ignores any possibility of dependence between the cells. So dependence is a whole complicated and interesting issue that we don't have a ton of time to go down that route right now. But roughly speaking, what dependence would mean is if there was a bad month for mortality, say like right now, but in the past, maybe just even a bad, the flu season varies from year to year. So 2017 was a bad one. 2018 was pretty mild. I hope I got that right. So when there's a bad flu season, for example, the death rate for both men and women will go up. Men and women can both get the flu, of course. It may not go up by exactly the same amount, but it'll go up for both sexes. And it will go up in most age bands. It won't go up in all age bands equally because the flu, like COVID, infects people of different ages to different extents, but it will affect different age bands to some extent. And so what that means is that a bunch of rows of our data matrix here will move up and down together according to these environmental factors. And that is statistically induces dependence between the rows of your data matrix. So the rows of the data matrix, if I didn't make this clear earlier, are months, historical months. So our data is going to be aggregated. This is just from the previous page. The data are going to be aggregated by month, by year, by sex. So the rows of the data matrix would be like, and also by age band. So it would be exactly what you see on the previous slide. So the point is, a pure GLM, there should be no statistical dependence between the rows of the data matrix. But we have very good reason to believe that there must be statistical dependence between the rows of this particular data matrix because of what I just described. A bad month will cause many death counts to go up together. A good month will cause many death counts to go down together. There could also be serial dependence because if January is bad, January of say 2007 was bad, then February of 2007 is probably bad as well. So there can be both serial dependence and cluster-wise dependence. So there's a lot to be said about the dependence structure in these data, and that would be an interesting topic. That could be a whole workshop on its own. or a direction for people to pursue. I'm going to largely ignore that and just do the basic due diligence so that I can at least say that I've accounted for dependence in some minimal way. And so that's what happens in cell 6. In cell 6, I use this technique called GEE, generalized estimating equations, that you may or may not have heard of. It's really just GLM with some extra window dressing on it. And what it does is it accounts for certain forms of dependence in the background while still making like you feel like you're fitting a GLM. So it's very nice if you just like GLMs and you don't want to switch to something more weighty like multi-level Poisson regression or Glm type analysis. You can use GEE, and it feels like you're using GLM, but you're actually doing something extra to account for the dependent structure. So I actually really like GEE, and here is a place where I'm using it. The regression formula is the same. I'm fitting the exact same mean structure. It's just that there's some extra stuff happening in the background to account for the fact that I'm allowing there to be some dependence between the rows of the data, as I just discussed. That's in cell 6. And then cell 7, I'm going to skip over some of this because I can see I'm probably going to run out of time. So don't worry about that particular graph there. So cell 9 is another GEE fit. I'll say a little bit about the plot on the top of this slide in a minute, but before we go there, cell 9 is another GEE fit that looks at a different type of possible statistical dependence among the rows of the data frame. So this one groups by age group and looks for stationary for temporal correlation or serial correlation within each age group over time. The one in cell 7, I think it was 6 actually, the one in cell 6 groups by historical month and looks for common correlation among the age bands within that month. So it's just two different ways of trying to capture some of the dependence. And a thorough analysis, you would actually look carefully at the data to see which one fits better. But I don't want to, that's a different skill for a different day. So I want to kind of largely ignore that. And I'm just going to go with the model in cell 7. I'm just going to, like by fiat, go with the model in cell 7. But there are tools out there, QIC and so on, that one could use to judge more formally whether the model in cell 7 or the model in cell 9 or yet some other model is the right way to handle the dependent structure of these data. But again, in the interest of time and wanting to get on to the other things, I'm going to largely suppress that for the rest of this discussion. So I'm just giving you the seed here that you could use to pursue that direction more thoroughly. I'm not going to go there myself. Okay, so everything, so 9 is actually a bit of a digression. Everything subsequent in this part of the talk is going to be built on 7. Let me just briefly discuss this slide, the plot at the top of this page. So this is plotting standard errors for the GE analysis versus the standard errors for the GLM analysis. And the point here is that they're different. And they're different in a fairly complex way. And this is typical. That's actually the whole point, is that when you have dependencies in your data, if you only want to make predictions, or if you only want to interpret the parameter estimates just numerically, you could actually use a GLM and just ignore the dependence, ignore the statistical dependence. That's actually okay. Maybe not optimal, but it's okay. But if you want to do statistical inference and talk about how confident you can be with any findings or do any kind of testing or formal statistical analysis, you can't do that. You can't just ignore the dependence. And so GEE does the right thing. It looks in the data in a more careful way and figures out what the proper standard error should be given the degree of dependence in the data. And so that's why the standard errors here are different between the GE and GLM analysis. So there's a lot that could be said about exactly why some standard errors are bigger in GLM and others are bigger in GEE, but that's a more advanced topic that I won't get into further today. Okay, so now let's just focus on the mean structure. That's the most interesting, the most tangible, the easiest to relate to and interpret relative to like the real world. It's not so statistically technical. So let's move on to this section. It's 0.3 on the PDF that says models with interaction. So we're now going to move to a little more sophisticated mean structure here to tease out like more interesting behavior in these data, because I don't think in the end, and the data are going to tell us this, that the purely additive model is correct. It's always confusing, just to make this clear one more time, is that when I talk about an additive model in a Poisson regression, because the Poisson regression uses the log link function, an additive model is really a pure multiplicative model, as opposed to something that's even more complex than purely multiplicative. So sometimes I might say additive, other times I might say pure multiplicative, but in this context, we mean the same thing. Okay, so check out cell 11 now. And again, think of cell 11 as being like the follow-up to cell 7. So cell 11 is a regression formula that now has an interaction in it. So star is interactions, plus is just additive. And so what we're going to do here is we're going to allow the age group effects to differ by sex. So what does that mean? So the age group effects are really important, of course, and people who are 80 are far more likely to die than people who are 30. And so the age group effects capture the profile of death risk, mortality risk over the ages. And when you interact that with sex, you're basically saying that the shape of that profile is different for women and for men. It's not just that men of all ages are, say, 5% more likely to die than women of all ages. It's saying that the actual shape of the detailed age-specific mortality risk differs between women and men, if you include this interaction. So that seems plausible. Like men and women die of different things, and of course die at different rates and different ages. So it seems plausible that it would not be a pure multiplicative effect, that there would be more going on between age and sex than just a scaling effect. And so the model in cell 11 is investigating that. So I'm showing you basically here how you can build more and more complexity into a model by iteratively adding more and more interactions. And so, and then you can always say, well, I could do that and add arbitrarily many interactions into a model. How do I know when I've gone too far? So that's where we need some statistical guidance. So what I'm going to use here for the model guidance, model fitting guidance, sometimes people call it model selection, is this thing called a score test. Definitely not going to get into the theory of what a score test is. Just suffice it to say that a score test is a rigorous way to judge whether a bigger model is actually a better model, or a bigger model is simply overfitting the data and is not actually a better model. That's the goal of score testing. And so, and it's quite easy to do in this package. So if you look at the top of page 6, I guess it's just what the output of cell 11, there's a p-value there. 0, it just prints out to 0. It's not literally 0, but it's essentially 0. So that basically means, so the null, that's the p-value for the null hypothesis that the sex and age group do not interact. That's the null hypothesis, that sex and age group do not interact, against the alternative hypothesis that they do interact. So p-value of 0 means you strongly reject the null. So there's very strong evidence for age by sex interactions. So that's interesting, but of course you really want to say, well, what is the detailed structure of that interaction? So we're going to come to that later through graphics. But for the moment, I'm just going to walk through a series of ever-increasing models and see how far we should go, guided by the score test, until we take it too far. So in cell 12, I now add a month by sex interaction. So the month effect is the seasonality. There's a seasonality to mortality. More people die in the winter and fewer in the summer. We'll see that in a minute. If you interact that with sex, that means that the seasonal pattern of mortality for women is different from the seasonal pattern of mortality for men. It's plausible that that's the case, but we don't know for sure until we check it. So in cell 12, we compare this model to the previous one, and the p-value is 10 to the minus 8. So there's very strong evidence that the seasonal pattern of mortality is different for women and for men. Note that each time I discover something, I leave that new thing in the model, and then subsequently that becomes the base model that I'm testing against. So in cell, it was 11, I established that there's an age by sex interaction. So now that age by sex interaction is going to stay in the model forever. In cell 12, I established that in addition to the age by sex interaction, there's also a month by sex interaction. And now that's going to stay in the model forever. And you can probably see where this is headed. In cell 13, I look for an interaction between year and sex. And let me say a little bit about what year sort of means. So the year effect is, I usually refer to this as the long-term trend. So mortality, like I said, has been generally trending downward since World War II, faster and sometimes slower in others. So basically, the question there is that if there's a year by sex interaction, that means the long-term trend in mortality for women and men are different. And again, we've got a ridiculously small p-value, 10 to the minus 11, which indicates that there's very strong evidence for a year by sex interaction. So the model in 13 has interactions between sex and everything. So basically it says women and men are different. Females and males are different in in terms of the seasonality of their mortality risk, in terms of the age specificity of the mortality risk, and in terms of the long-term trend of the mortality risk. That females and males are different in all those regards. Okay, so that's where we are now from score testing. Now, if I push it one step further, and now in cell 14, I say that I add an interaction between year and month. So this would say that the seasonal pattern, I am allowing the seasonal pattern to differ by year. And now the p-value is actually 1 in the output to cell 14. So there's no evidence from this analysis that the seasonal pattern of mortality differs by year, because I got a p-value of 1. We could also look for age group by year interactions, and I think that also gives us a p-value of 1. Now, I'll tell you, I actually believe that in a sense that p-value is misleading. So I believe that there actually is an interaction between year and month. But when we treat year and month as dummy variables, so there's like 12 year indicators and 12 month indicators, then that creates a lot of parameters. It's basically saying that there's an arbitrary change in the seasonal pattern from one year to the next, and you have to back that change out from the data that we observe, which is, there's not huge numbers of deaths, of course, in many of the age bands, so you don't have tons of power to identify very subtle shifts. So I think the issue here is that treating year and month as factors and has some advantages and has some disadvantages, but one of its disadvantages is that you have almost no power to detect a year by month interaction. In fact, I believe there is a year by month interaction, but we have no power to detect it. So the solution to that, one possible solution to that, in my view, would be to model year and month with splines, which would reduce the degrees of freedom, instead of modeling year and month with indicators, which has more degrees of freedom. So splines are a really useful tool. We have workshops at CSCAR on splines. I just didn't want to throw too much at everyone today, so I'm not going to pursue that direction today any further, but I just wanted to mention that that's yet another thing that people could try. Stats models support spline-based analysis very well, and there's syntax that you can put into that formula in cell 14 so that the interaction between year and month would be parameterized through splines instead of through indicators. And my guess is that you would find an interaction if you pursued it that way, but we're not finding it here if we pursue it via indicators. And that's okay. For what we want to do next, we don't need to maximize the complexity of this model. It's okay. We're going to stop on cell 13 and have that be our final model. But like I said, I think you could push this even further by using splines. Another way to push this further is using PCA. So that's what I really would rather focus on. So I'm going to let model 13 be our final model for the GLM part of this workshop. And but we will see once we switch over to doing PCA, we'll see that some new things emerge in the PCA that the model in cell 13, that's model 6 in my numbering here, didn't succeed in picking up. So it picks up a lot, but it doesn't pick up everything. Now where we are now is we've got this nice complicated model. It's got probably like, I'm trying to count here, maybe 50 or 60 parameters in it. So that's quite a complicated model. But we don't really know anything about the model. We just know that the score test told us that this is the model to use. So let's now make some graphs so we can actually see what this model is telling us. So again, it's model 6 that we're going to be looking at here. The graphing, unfortunately, involves like a certain amount of ugly coding to get the data lined up in the proper way to graph. So I'm going to not talk about the code, just jump to the graph. Okay, so here's what we got for the basic age trend for males, the risk trend for of mortality risk trend for age for females and males in this plot on the bottom of slide 7. But I think everyone knows the basics here. Common sense is that we know that older people are more likely to die than younger people, and at every age, women are more likely to die than men. The age trend is the one exception to that age trend, to that increasing age trend, is that very young children, there's actually more mortality for very young children. Infant mortality, we know, is a problem. So there's more mortality for children under 5, and then it drops. So you're at your lowest risk of dying when you're between 5 and 10, and then it slowly increases almost linearly on the scale all the way through to the end. And then at any given age, again, men are more likely to die than women. and this is relative to the population size. So it's not like, you know, penalizing a group just because there's more people in that group or fewer people in that group. Now, the way to interpret this graph, it looks a little bit weird. It says log risk ratio for deaths, and then you have negative numbers and so on. So what's the right way to interpret this graph? The way to interpret this graph is you can take any 2 points on these curves, either any 2 orange points, any 2 blue points, or 1 blue point and 1 orange point, either at the same age or at different ages, and then subtract them and exponentiate the difference because of the log link function, the Poisson model. And that will tell you quantitatively how much excess risk there is for mortality in one group relative to another. So let me do that more by example here. So let's look at age 40. And the female number there is like 0.2, and the male number is like 0.8, let's say, just eyeballing it, above 40. So 0.8 minus 0.2 is 0.6, and e to the 0.6 is like 0.7 or 0.8. Sorry, 1.7 or 1.8. So that means that at age 40, men are about 70% more likely to die than women at age 40. So that's the way you would actually interpret this graph, is you would take differences according to whatever groups you're interested in, subtract 2 points, and then exponentiate the difference, and that will give you the risk ratio. That's what epidemiologists call it, the risk ratio between those 2 groups. Just eyeballing it, what you can see is the interesting thing is that the gap emerges at age 20 and then flattens out. So there is this well-known fact that young men are especially likely to die of mainly of accidents. I mean, your risk of dying of diseases like in your 20s is very low, but a lot of people in their 20s die of accidents and injuries and even violence, and that's heavily concentrated in men. So the big gap there, the rapidly increasing mortality in men from like age 15 to 30 is due to that. And then once you get past the ages where injuries and accidents are very prevalent, you just have the usual age-based disease-driven effects kicking in, and men and women increasing roughly in parallel. So that's already we've learned something. And if it's too much, if that last graph was too much, we can simplify things a little. We can just take the point-wise difference between the male and female risks, log risks, and I don't exponentiate it here for you, but I just take the difference, and you can see again the spike in mortality from excess mortality, we can call it, excess mortality for men over women relative to women in the 20s. It comes out here quite prominently. So men are more likely to die than women at every age group band, but it's dramatically so at age 20, you know, because it peaks out at around 1, and e to the 1 is 2.7, call it 3. You know, at that age band, men are like 3 times more likely to die than women. So it's quite a large difference. It's a very large 300% change in the death rate. So of course, deaths in your 20s are rare, relatively rare, far more rare than deaths in your 60s. But in that rare set of the spectrum, the ratio between men and women is extremely high, 300%. So these are from the model. If that's not clear, these are from the model. I'm not simply plotting raw data here. These are predicted values from the fitted model that we went to some effort to fit earlier in this discussion. And that's kind of the big picture here, is that you fit a model, the model like smooths out the data, extracts the trends that are real, suppresses the trends that are just noise, and then you study the model through graphs. It's much more informative to study the model through graphs than it is to study the data directly through graphs, because the data can be quite noisy. The model is supposed to represent like the true population structure, not just the random events of individual deaths. Okay, let's talk about seasonality now. So this plot on page 9 of the PDF, it's below cell 17 if you're following along in the notebook, shows the seasonality pattern. What is the seasonality pattern? Well, this is well known, I think, is that there are more deaths in winter and fewer deaths in the summer. It's the amplitude of that seasonal pattern is around 15%. So it's not like 300% like we saw before, but there's still, it's noticeable, 15% more deaths in, say, January compared to June. So that's driven by various things, largely, I guess, by disease like influenza. Diseases, respiratory diseases that spread around in the winter. There's an interesting going on here. It's very well known that it's in the death rates are particularly high in December, that's month 12, and January, that's month 1, and then it drops in February, but comes back up again in March. That's not just noise, that's real. I mean, it happens independently in the females and males, so that strongly suggests that it's real, it's not noise. And there's a lot of research on this. It's known for, it's not exactly known how this actually is actualized, but some people strive to survive through the holidays, and then January hits and they die. And so in February, that effect has dissipated, but the flu season is still going on. So then in March, you get a lot of influenza deaths. So I'm sure there's more to it than what I just described, but that's kind of a high level idea there. Now, we showed earlier with our score tests that the seasonal pattern of deaths is different for women and men. But actually, if you look at this graph on page 9, it's not super obvious that the seasonal pattern for deaths is different for women and men. But statistically, it is. Of course, the males have a higher death rate than the females, but the shape looks similar, but actually it's not. The shape is flatter for men than for women, which means that men have a less seasonally driven pattern of death than women do. So men are less, the gradient of deaths between winter and summer for men is weaker than the gradient of deaths between, for women, females between winter and summer. The reason for that likely is that injuries and violence are concentrated more in the summer. And so for men, that kind of takes over. So you don't gain as much from the end of the flu season for men as you do for women. That's at least the story that I've heard here. I'm not a demographer. I'm not an expert in this. I'm just telling you what I've heard. So they're largely parallel, but they're not perfectly parallel. And this next plot on page 10 shows that the male-female risk ratio is seasonal. It's not constant. That's why there's this strong interaction between sex and month that we saw earlier in the GLM modeling. And the pattern is that it peaks in the summer. So that's, again, driven by violence and injuries. And now let's talk about the long-term trend. So the long-term trend is mostly down. That's good. Mortality rates are decreasing. And it was going down nicely for a while. And then there was actually a lot of discussion a few years ago about flattening out of the mortality gains, and perhaps driven by opioid deaths. And it possibly even for the first time in modern history, the life expectancy in the US was actually going to decline, or did decline a little bit for 1 year, I think 2017, or I'm not sure if I have the year right. Now, this is not life expectancy. That's a whole other issue, is how you get life expectancy out of mortality data. We're not looking at life expectancy. We're looking at death mortality risks, but they're obviously connected. And so I think that flattening out or even increase in men between 2013, 14, and 15 is quite possibly driven by the opioid epidemic. The opioids affected women and men, but I think it affected men more than women. And the only good thing I can say there is, at least by 2018, it seems to be declining again, but of course COVID affects men more than women, so who knows what this will look like in a couple of years. So that is the long-term trend. And again, these are not statistically parallel. I mean, they're not perfectly parallel. The orange line is not just the blue line shifted up by an inch. Its shape is different. And the reason that the shape is different is because we included those interactions in the model that allowed their shapes to be different. If we had not included an interaction between sex and year in the model, then this plot would actually be kind of boring. It would be the exact same curve translated up and down by a certain amount. It wouldn't even be worth making the plot. So it's only because of the interaction that we see this non-parallel behavior emerge. So I think, like, thinking about interactions, what they mean is, I can tell you from doing consulting for many years, is that this is one of the things that people really struggle with in terms of interpreting regression models. And there's some, I think, slightly misguided notion that like machine learning just solves this for you and you just throw your data into the neural network and everything comes out magically. If you're doing predictions, that may be true to some extent, but if you want to understand relationships, I think there's just no way to get around parsing out the effects driven by different factors, what's parallel, what's not parallel, and it just takes a lot of practice to do that. So I hope this notebook is giving you some insights into one way to approach this type of modeling. This is what I personally like to do, regression analysis with this type of data. There's a lot more that could be said, but I think in the interest of time, I'm even going to skip. I really like the analysis on slide 13 or page 13. Basically gets back to this question of justifying that these data really do meet the minimum assumptions for analysis with quasi-Poisson regression. But in the interest of time, I'm not going to go through this. You can read this on your own if you're interested. But obviously, I didn't, I said this earlier that GE, GLM are quite robust, but they're not infinitely robust. So you still want to make some checks to make sure that you're not barking up the wrong tree with the analysis. Okay, so I'm going to unshare this document, and this will be a great time for people to ask any high or low level questions that they have. And then I'm going to share a different document, which will be the next part of the workshop. Anyone want to either speak up or send a question via chat for us to talk about now as we take a very short intermission between the two parts of the workshop, the two main parts of the workshop? I assume people are still out there. I can't even tell. I'm like talking into the void, but I guess I'm getting used to that. Okay. Yeah, that would be fine. If someone wants to speak up, totally fine. Month and year is categorical instead of numerical. Yeah, so that's a good question, and that's a judgment call. And actually, I use splines all the time. I wouldn't treat them just as purely numerical. I would treat them as numerical and then use splines. And so probably in other settings, I may very well have used splines. Now there's a little bit of a tricky issue with the months because months, of course, are cyclic. So month 12, what comes after month 12 is not month 13, but rather month 1. So you have to use this thing called periodic splines. And that brings in a bunch of other rigmarole. So for this analysis, I chose to essentially stay closer to the data and treat month as a categorical variable, which I know is kind of weird because you know that April is closer to May than it is to November. We have enough data. We actually have enough data to do it this way, to do it with factors. But you could also benefit, I think, from using splines. And like I was saying earlier, you could possibly successfully extract more interactions with splines than I was able to extract with indicators. But it would require a little more work because you'd have to get some kind of periodic spline in there for the seasonal effect. And then you have to decide on the degrees of freedom and so on. So splines are really useful. It's just for this workshop I left them out, but they're one of my favorite tools. It's probably the most important thing I use that's not making it into this workshop today. Okay. Thanks, Daniel, for that question. Okay, so if there's no more questions, let me switch over to the PCA thing because we don't have tons of time. I'm just going to keep it simple and go with the PDF. Seems to be working okay. So I got to find it in the mix of all my junk here. More PCA.pdf. Okay, so this is the PCA part of the analysis. So this is in some ways more interesting to me, but I'll tell you why in a minute. So principal component analysis, like I said, is one of the mainstays of applied statistics. Now, this is actually not that PCA. This is a different PCA. So this is actually GPCA, generalized PCA. And the G in generalized PCA is the same G in GLM. So generalized linear models, generalized PCA, the G is the same for those two techniques or classes of techniques. And the point of that G is to deal with a much broader range of data relationships than you can get out of like a more linear type procedure. And it's really about the key thing here is what we call the mean variance relationship. So the mean variance relationship tells you how does the variance scale with the mean. So for a lot of data, including mortality count data, I'm sure, the variance is an increasing function of the mean. Whereas the more simplistic models like traditional PCA, Hotelling PCA, if you want to call it that, after the guy Hotelling who supposedly invented it, but they probably really didn't. They are optimal for situations where the variance is not related to the mean. It has nothing to do with Gaussianity. I think Gaussianity is sort of a red herring in a lot of this stuff. But just like least squares, the variance and the mean are unrelated, but in Poisson regression, the variance is an increasing function of the mean. In GPCA, the variance is an increasing function of the mean. And so when you have data that have that property, have that mean variance relationship, you'll probably get more out of it by using GPCA than PCA, just like you'll probably get more out of it by using GLM than OLS. OLS stands for ordinary least squares, or just the basic way of fitting linear models. So that's what I've done here. Now, GLMs, like I said earlier, were invented in the 70s, and they're a standard tool that's available in all statistical packages. GPCA, surprisingly, actually was proposed like in the year 2016. So it's actually quite a recent invention. Now, historically, there are various other proposals out there to do PCA on non-sort of homoscedastic data. But this one, I really like this one. This more recent proposal, I really like. And it wasn't even implemented in Python, so I had to implement it for this workshop. And so I will eventually merge it into that stats models package. I'm a maintainer for that package, so I'll merge this into that package. But right now, I just implemented it for this workshop. So that's in the Python directory of the GitHub site in a file called gpca.py. So that's the code to actually implement this procedure. It's not actually particularly easy to implement. I have to say, I struggled with it, but I think I got it right. And so I'll merge it into stats models later on, like in a month or so, probably, once I've done a few more things with it. So I wouldn't call it a standard technique, but it probably deserves to be a standard technique, because just like we have linear models and generalized linear models and PCA, the piece of that puzzle that's missing is GPCA. So I think it deserves to be out there. I don't think the properties of it are like as well elucidated as the properties of PCA are. So I'm using it now and just kind of having faith that it gives meaningful results. I think it should. But maybe people need to study its properties a little bit more. That's what statisticians do, is they study the properties of data analytic techniques to make sure that they don't mislead us. But I think this one should be fine. Okay, so basically we can just pretend we're using PCA. So the nice thing about GPCA is once you decide what family to use, we're going to use the Poisson family, then you just run it and you're just like doing PCA. So the interpretation, the story that you tell out of the results is very much like the story you would tell from a PCA. It's just that you doing the PCA in a way that's more appropriate given the nature of the data, which has this Poisson-like mean variance relationship, or quasi-Poisson-like mean variance relationship. Okay, so basically what this means is we're looking for factor structure. So we're trying to find profiles, and this is always a challenge when I teach this stuff, mainly to master's students in our program. It's always a challenge to get people's heads wrapped around what PCA is really doing. I mean, everyone thinks they understand PCA, and I don't mean to cast aspersions on people, but I think a lot of people who think they understand PCA understand it only at a superficial level, because it's not easy. And it's trickier than just like a mean comparison or a regression model, because it's really fundamentally about variation rather than means. And variation is harder to talk about and wrap your head around the means. So if you've studied factor analysis, this will all be very natural to you. But if you haven't, maybe you've used PCA, but people sometimes just use it for dimension reduction. And that kind of really is just scratching the surface, in my view. The value of PCA is to actually do modeling, is to learn what the data are telling us about the system that the data were collected on, rather than to just simply reduce the dimension to make the data smaller. So what that means is, well, let's see. What that means is it can reveal some things. It actually is, it can almost be viewed as a sort of a non-parametric approach to understanding what's going on in the data. So like we went through all this effort earlier today with the GLMs, kind of adding and removing factors to try to find the model formula that gave us the best structure. And that maybe you found that to be kind of tedious. I don't mind, but some people might find that to be kind of tedious. They want something more automatic. So in a way, PCA is in some ways, a more automatic way to analyze data. So that's actually, that's a feature, I think, of PCA. Okay, so what are we going to do here with this PCA? We're going to, first off, I'm going to analyze men and women separately, males and females separately. There's so many differences between the mortality behavior of women and men that I actually initially tried to analyze them together, but it just was not convenient, not informative. So I decided to split them apart here, split the females and males apart here, and I'm going to analyze the females and males separately, so we can focus on the time trend. So what is PCA all about? So what PCA is, you think of PCA as doing is, first off, you typically think of PCA as applying to a data rectangle. And the rectangle, the data rectangle that you apply your PCA to, is the columns are variables and the rows are observations or cases or units. So for what we need to decide for us, what's going to go in the columns and what's going to go in the rows. So that involves like essentially pivoting our data. We had the data in long form for the regression analysis, but we need to pivot it back to like quasi-wide form for the PCA. And I'm going to pivot back the age groups. That's a choice. It's not like the only choice. It's just a choice. Pivoting back the age groups means that I'm studying the structure, the age structure of mortality. I'm going to focus on the age structure of mortality, just to focus in on one thing here for the purpose of this lecture. Now, you could have focused in instead on the, you could have pivoted on this, on the months, and then you would have been focusing on the seasonality of mortality, which actually is very interesting. And a student working with me did this and showed me what she got, and it was very interesting. You could even pivot or unpivot on the years and look at the long-term trends. But I'm going to pivot on the age groups here just to keep it focused. So basically what that means is I'm going to have a data matrix for females and a data matrix for males whose columns are age bands. Remember, there's 18 age bands, and whose rows are essentially are temporal cells. A temporal cell is essentially a month, a historical month. So we have 12 times 12. It's a coincidence that it's both 12. I have 12 years and 12 months, 144 rows and 18 columns because we have 18 age bands. And we have that matrix for females and we have that same matrix for males. The values inside of the matrix are counts, the number of people who are observed to die. It's the same data we were working with before. It's just structured in a different way. And just like before with the GLMs, we want to really be thinking about death rates, but we don't actually want to divide deaths by population. So we're going to have an offset again. And actually the terminology and the underlying mechanics actually of GPCA borrow a lot from GLM. So just like you can have offsets and link functions and families in GLM, you can have offsets and link functions and families in GPCA. They work essentially the same way. So I'm going to use population as an offset, or technically it's log population as an offset, so that, again, the results should be interpreted as death mortality relative to population, not absolute mortality. Okay, so we do that. We have in cell 5 here, we do that for women and for men separately. And you may know from your earlier work on PCA is that there's this choice you have to make in terms of how many factors to extract. And if you want to be very formal about it, you can make scree plots and all kinds of things like that. I'm going to not do any of that today. I'm going to forego that and just declare that we're going to extract 2 factors. That's just the maximum I have capacity to think about. It's already complicated enough. But if you had more time and more interest, you could probe beyond. There's very likely more structure than just 2 factors. So here in cell 5, I'm doing this. I have a loop that loops over females and males. I pivot the data or unpivot the data and get the GPCA fits for females and for males. Couple comments. One is, I'm going to talk about this more in a minute, but it turns out that there's classical PCA. Earlier on, I said it's often attributed to Hotelling. Harold Hotelling is a statistician that was working like in the 1920s and 30s, or maybe he was an econometrician, I'm not sure. But anyway, he's often given some credit for PCA, although it probably goes back earlier. This idea of functional PCA emerged like in the 1990s, and functional data analysis as a branch of statistics emerged in the 1990s. Basically, people wanting to get more out of data by imposing smoothness on things that naturally should vary smoothly. So if you're estimating a function, the logic of functional data analysis is sometimes abbreviated FDA, is if you're estimating a function, treat it as a function. A function is not just a set of numbers, it's a function. So it should be continuous. It should probably have some smoothness to it. So these people figured out in the 90s how to do functional PCA, principal component analysis that is functional because it respects the continuity that's expected and the smoothness that's expected in the factor structure. So what I've done here is I borrowed ideas from them and mixed it up with these ideas around generalized PCA to create functional generalized PCA. Because of course the age bands are ordered. There should be some smoothness to the mortality behavior. It's not that different to be 55 and 60. So there should be some smoothness there. So that's what's going on cell 5. I fit the GPCA with and without the smoothness penalty just to illustrate what the smoothness penalty does. So that PenMat argument induces some smoothness, and let's not worry now about exactly how much smoothness I'm inducing. I'm just inducing, let's just say, a moderate amount of smoothness. And then above it, I'm not inducing any smoothness at all. If you have tons of data, then you can just let the data speak for itself. You don't have to force it to be smooth. It'll just be smooth. But we're not like, face it, we don't have tons of data. We have 144 rows and 18 columns. So that's not necessarily enough data to ignore like the side information that that this functional GPCA gives us. The last comment I'll make on the cell 5 is that I did cut off the iterations at 500 because I didn't want to sit here waiting forever for it to run. And it didn't converge, although it almost converged. So if you weren't doing this like in a workshop setting, the max iter equals 5,000 is what cuts it off early. You can take that out and you'll get fully converged solution, but it might take like 5 minutes to run. And while I was developing these materials, I didn't want to wait 5 minutes for it to run. So it's not a huge deal. I think you get essentially the right structure. It's just the fourth decimal place is going to be a little bit different. Okay. So that's just the mechanics of how you fit the PCA. I think I still need to speak a little bit more about what the PCA procedure actually gives us, but that's the mechanics of how you fit it. Excuse me. So there is an R package, by the way, for this, but the R package wouldn't do the smoothing. I don't think anyway. Okay, so what do we get out of GPCA? Well, basically you get two things. You get intercepts and you get factors. Just like in PCA, you get means and factors. In GPCA, you get intercepts and factors. And the intercepts are essentially analogous to means. Now in PCA, you don't normally care very much about the means, but they're there. And in GPCA, we're not going to care too much about the intercepts, but they're there. And so the intercepts, let's just get this out of the way. The intercepts are plotted on slide 3, or the bottom of page 3, and it should look very familiar. It's almost exactly the same as the age-specific mortality pattern that we got out of GLM. Because we've made the executive decision to do our GPCA against age, therefore the intercepts refer to the sort of base mortality by age. And I'm doing this totally separate by sex, but I can still plot the sex-specific intercepts on top of each other. And so that's what I've done here. So the story on this is exactly the same as the story on age-specific, sex-specific mortality that we got out of the GLM. I'm totally going to not talk about the coding details, but I write these utility functions like plot intercepts that do all the work of making the plot. So if you like to study code, that's there. But I just want to focus on the high-level methodological story here. The reason that it's really important to at least be aware of these intercepts is that PCA, this is what I was alluding to earlier when I said people struggle to really interpret PCA, and I agree it's not super easy. PCA is all about deviations from the mean. PCA is a methodology for describing deviations from the mean. The mean is like the crudest possible statistical summary of data. And once you've learned what you can from the mean, which is often not very much, it's natural to ask what else is going on in the data set. And so the first thing you might ask yourself is like, well, what are the common patterns of deviation from the mean? Because all the data, of course, don't always fall right on top of the mean. They vary from the mean. I mean, that's why we have statistics. So the deviations from the mean can behave in different ways. So, but because it's a deviation from the mean, those deviations from the mean have to wash out to 0. So if every time there's say a unit that is above the mean, there's got to be some other unit that's below the mean. It's like all the children can't be above average. You can't have all the data above the mean. So that's what makes this a little bit difficult to understand. But we'll continue this discussion here in a minute. The point is you have to understand what the mean is so you know what the deviations are to be interpreted against. The deviations that we're going to be looking at here are interpreted against the means plotted at the bottom of page 3. We'll continue this discussion by looking at the factors. So let's look at the factors. I'm going to skip over page 4 and go straight to page 5. That's cell 10, the results of cell 10. So these are the factors, and I'll tell you what that means if you don't know what I'm talking about here. For females, remember I said I'm going to extract 2 factors, so there's 2 curves here corresponding to the 2 factors. The blue is the dominant one. These are ordered, so the blue one is, I guess, more important than the orange one. And this is again for females. So what do these factors mean? So what happens with this PCA, GPCA or PCA equally, is that every unit of analysis in your data set, and the units of analysis in our data set are historical months, has a score associated with it. Actually, it has a score associated with each factor. So like March of 2009 has a score for factor 1 and it has a score for factor 2. And essentially what those scores tell you is the data for that month, March of 2009, deviated from the mean either in the positive or negative direction with respect to factor 1, and either in the positive or negative direction with respect to factor 2, and by a certain amount, a certain magnitude in both cases. And those scores tell you what the deviation was, what direction and how strong it was. So the way it's the language, it's almost like a template of language that I use. And once you get the language right, it all kind of makes sense. So if a historical month has a positive score for factor 1, that means it had more mortality for all age bands from age 10 and up. It's very important to notice where the zero axis is on the factor scale there. See how the 0 is right in the middle of the graph, of the vertical axis, that 0. So the blue curve is almost entirely above 0. Just the first age band is below 0, the first two maybe. So what this means, again, continuing what I started to say a minute ago, is that a historical month that has a positive score for factor 1 has more mortality in every age band above age 10, but especially in the 20s and beyond. Right, so that's the pattern of deviation from the mean that would be seen in a historical month that has a positive score on factor 1. And again, this has to wash out. So for every month that has a positive score on factor 1, there's some other month that has a negative score on factor 1. And that means for that month, the exact opposite is seen. So it's a historical month that has a negative score for factor 1 has less mortality across the board, or at least for ages 10 and up, especially in the 20s and early 30s. So that's the pattern captured by factor 1. It's essentially a pattern of higher or lower mortality. So you might imagine that winter months would have higher scores on factor 1 because you have more mortality in winter months. Now, what does factor 2 mean? So the key thing here again is to keep track of where the origin is. So the origin now crosses like right through the middle of the orange curve. So the orange curve is like half above the origin and half below the origin, or it's half positive and half negative. Unlike factor 1, which is almost all positive, factor 2 is like half positive and half negative. So what that means is that factor 2 it has a totally different interpretation. It's playing in a totally different role. It doesn't modulate the entire mortality pattern up and down the way factor 1 does. Instead, it shifts the distribution of mortality among the different age bands. So a positive score on factor 2 corresponds to increased mortality above age 50 and below age 10. And a negative score on factor 2 corresponds to increased mortality between age 10 and 50. So again, factor 1 is moving all mortality up and down, and factor 2 is shifting the mortality around within the age bands. And this is emerging, again, this is essentially a non-parametric technique. So this is emerging naturally from the data. I didn't like specify by any kind of spline or quadratic or interaction or anything what these curves would look like. They look like what they look like because that's what the data wants them to look like. So it's a more non-parametric technique in that sense. That's for females. For males, it actually looks quite similar. I'm not going to dwell on this, but if you kind of bounce back and forth, there are some minor differences, of course, but the male and female factor, these are called the factor loadings. Male and female factor loadings look quite similar. The scores will be different. We'll get to scores in a minute, but the factor loadings look quite similar. Now, just to go back to this notion of regularization or functional GPCA as opposed to non-functional GPCA, this on page 7, slide 12, or cell 12 and 13 is what you get when you don't do the smoothing. So, I mean, you could probably tell a story out of this 7, and then the one for males is here. Maybe it's even not that different from what the regularized one gives us, but it's actually much less like convenient to interpret because all of the zigzagging back and forth. And given there's a bunch of theory about the convergence rates of SVD-like algorithms. So this actually isn't an SVD-like algorithm, but it's sort of in the spirit of that. There's a bunch of theory by Ian Johnstone and others about the convergence behavior of SVD-like algorithms. So we actually know that these algorithms can give you essentially nonsense if you don't have enough data. I mean, regression can also give you nonsense if you don't have enough data, but more so for these FCD type things, factor type analyses. So you have to have enough data, or if you don't have enough data, you have to bring in some side information. So essentially what you should, the way I look at this anyway, is that the smooth version of generalized PCA is bringing in side information, smoothness, in order to make a more interpretable and probably more accurate result. And we don't know for sure that it's more accurate because we don't know what the truth is, but there's reason to believe from theory and elsewhere that the regularized versions of this GPCA are more meaningful than the non-regularized versions. So we won't look at the non-regularized stuff anymore. I just wanted to show you what they are so we can compare them to the regularized versions. But all of the discussions subsequent to this are going to be based on the factors that are shown in cell 10 for females and cell 11 for males. And these are, again, the regularized versions. You can see they're much smoother. So those are the factors. Like the scores and the factors are like dual to each other. You can't interpret the scores without knowing what the factors are. You can't interpret the factors without knowing what the scores are. So let's move on and talk more about the scores. So I'm moving up to cell 16. Excuse me. So cell 16 shows the scores for component 1 against the scores for component 2 for females. And remember what our data set consists of. It consists of months from 2007 up to the end of 2018. I've colored the points by month here, but so 1 through 12 there is month, January through December. Don't worry about that right away. So what is this going to tell us? So this is a scatter plot of scores against scores. So scores for component 1 against scores for component 2. If you remember a little bit of the basic theory of traditional PCA, you remember that it's a mathematically guaranteed in traditional PCA that the scores have mean 0 and are uncorrelated with each other. So scores for different factors. Traditional PCA comes from like an eigendecomposition, if you remember this. And therefore, that essentially guarantees that the scores have mean 0 and are uncorrelated with each other. Now, we're doing GPCA here, which is based on a totally different technique. Well, analogous, but different. And so the scores won't have mean 0. As you can see, they definitely don't have mean 0. And they won't be exactly orthogonal to each other or uncorrelated with each other, but they'll be pretty close to being orthogonal to each other. So there's no evidence of correlation in this plot. So that's something you would expect from any other experience you have with PCA in the past. Now, as ever, lack of correlation doesn't imply lack of structure. So it's not like just because a scatter plot has no correlation in it that there's no structure. Clearly there's structure here. The most notably what I see is that when the score for component 2 is small, meaning more negative, the scores for component 1 are less variable. They're more tightly concentrated around the middle of the range. Whereas when the scores for component 2 are large, they're more dispersed along the horizontal axis. And that doesn't contradict there being no correlation, because the correlation, well, that wouldn't induce any correlation. And that probably means something. We'll talk more about what that might mean in a minute, but that's just something I wanted to point out. So I just want to reiterate that we have to interpret this score plot remembering what the factors are. So remember the factors, what is the meaning of the factors? So a historical month with a large score for component 1, or for factor 1. Sorry, I probably should have used factor 1 there instead of component 1. This means the same thing. So a historical month with a large score for factor 1 would have more mortality across the board, except maybe in the very youngest people, but essentially would have more mortality across the board. Whereas a historical month with a smaller score for component 1 or factor 1 would have less mortality across the board. Whereas on the vertical direction, it's about the composition of the mortality. So with the historical months with a large score for component 2 or factor 2 would have a steeper age gradient. Let me make sure I get that right. I don't want to get it backwards. Yeah, a steeper age gradient. So a steeper age gradient means that the deaths are more concentrated among older people and to some extent among very young children. That's sort of the historical norm, I guess. I mean, it's not good or bad, but the historical norm is for deaths to be, for middle-aged people to not die, young and middle-aged people to not die. So the historical norm is for there to be a very steep age gradient, so the mortality is concentrated among the very old. And so oops, I wanted to be here. When the score for component 2 is large, then that month is exhibiting a very steep age gradient. So most of the mortality is in fact concentrated among the very young, the extremely young, and the old. Whereas when the score for component 2 is lower, you get sort of an attenuation or a dampening of that gradient, so that there's more than typical mortality among the middle-aged. So the mortality gradient essentially flattens out when the score for component 2 is small. That's the interpretation I place on these factors, having had the chance to think about them a little bit over the last few days when I was putting this together. That is, I think, quite interesting. It's actually part of what has been discussed a lot in the literature on the aftermath of the Great Recession and the opioid crisis, is that you had a lot of, I mean, it's not, generally speaking, it's not 80-year-olds who are overdosing on opioids, it's 20, 30, 40-year-olds. So you have a factor coming in, an external factor coming in, and modifying what would have been the historical norm for mortality. And of course, there's a lot of interest also in chronic diseases and like the obesity crisis. That the opioid crisis is largely over, but we have obesity and metabolic disorder crises also. So interesting questions about what that's going to do to the composition of mortality. Is it going to accentuate the age gradient, or is it going to attenuate the age gradient? That's, I think, questions that can be answered using these sorts of techniques. All I'm saying here is that there is a variance component in the data in which some historical months have a steeper gradient with respect to age in terms of mortality, and some historical months have a flatter gradient. In a minute, we'll see a little bit more about where those months fall. Where do the steep months fall and where do the flatter months fall? This is the analogous plot for males. It looks very similar, so I won't dwell on it. So to understand what these factors mean, I'm going to plot the factor scores against covariates or variables that I can interpret. So I know what a month is, I know what a year is. So in order to get some meaning out of these factors, I'm going to plot the scores against months and again the scores against years. So what do we see here? So let's look at this cell 19 plot. We see scores against month. So this is looking at the seasonality of the score, of the scores, basically. And these are the scores for factor 1. And remember, factor 1 corresponds to greater mortality across the board, essentially, for all age bands, except for maybe the very young. So you can roughly see a V shape here. It's not super pronounced. We'll see more strong seasonality actually with regard to factor 2 than with regard to factor 1. There is some seasonality here, right? There's a strong, the highest months are December and January, and March is also pretty high. And February and the spring and summer and early fall are much lower. So this is the historical norm in that there's more mortality in winter, possibly not February, but more mortality in winter driven by various factors I alluded to earlier, respiratory infectious diseases and seasonal, maybe some depression associated with the seasonal effects and so on. So that effect is clearly there, and we see it by just inspecting how the scores for factor 1 vary with respect to month. For males, it's a little bit noisier, but it's basically the same. There's more mortality. The highest mortality is still January and December. As I mentioned before, the males have a weaker seasonality to their mortality than females do, because males tend to die a lot of injuries and violence more in the summer. And so and then they continue to die of influenza and so on in the winter. So that flattens out the seasonality. So that's the story I would place on these two graphs. Factor 1 scores by season. Now, if we look at factor 2 scores by season, starting with the females, it's actually much more strikingly seasonal. And also, if you look at the colors, which correspond to years, it also has a very strong long-term trend. So we'll come back to the long-term trend in a minute. But with regard to the seasonality, this is actually more seasonal. This is a little bit surprising, more seasonal. Factor 2 is more seasonal than factor 1. So what this is almost telling us is that the seasonality of death is less reflected through the overall mortality rate than it is reflected in the way that mortality is distributed across the age bands. Right? Because remember, factor 2 corresponds to either a flattening or a steepening of the age gradient for mortality. And so this is the factor 2 scores are actually more seasonal than the factor 1 scores, which means that from winter to summer, it's not just that the total number of deaths increases in the winter, but even more so, the way that those deaths are distributed over the age bands differs in winter compared to summer. So that's something that would not be super obvious, I think, is this is one of those places where the extra complexity of using a more advanced statistical technique actually pays off. And statisticians are often sometimes criticized fairly so for like using fancy techniques just because we like them. But in this context, I think you would not necessarily have come away with this insight if you had not used a more elaborate technique. So that's very interesting that at least in the females, the gradient of death is very much stronger with age specific in the winter compared to the summer. And here's factor 2 for males, also very similar. So this is actually not a sex specific effect. This is true for women and for men. Okay. It's largely driven by deaths shifting towards the extreme ages in the winter, and then moving back to the middle age ranges in the summer. Now again, these deviations are deviations from the mean. These factors describe deviations from the mean. So I'm not at all meaning to imply that the absolute risk of dying for like a 40-year-old in the summer approaches the absolute risk of dying for an 80-year-old in the summer. That's definitely not true. These are deviations from the mean. The mean retains a very, very steep age gradient. It's just that that strong age gradient is moderated to some extent in one way in the summer and another way in the winter. And the factor structure tells us about that. Okay. Now let's look at, this will be the final thing we look at before we wrap up. Let's look at the long-term trends for these same scores. And so here we have the long-term trends for factor 1 females. So basically what this looks like is from 2007 or so to 2012, that component that captures overall mortality was declining, which is good. The scores for it were declining, which is good. But then they leveled out or even started increasing again, which is bad. And again, it could be the opioid thing. It could be increasing burden of chronic diseases, which are all kind of becoming increasingly prevalent. I'm not sure, but so I don't think it's good. We would want this thing to go down, not up. And for males, it's a similar story. It was decreasing until around 2013, and then it started increasing again. Although for males, as well as for females, I think in 2018, it actually started going down again. So maybe what will happen is it'll go down in 2018 and 2019, but then back up in 2020. COVID didn't hit the US until 2020, so the COVID effect won't show up until 2020. January, the lightest blue in these graphs is the one that's most impacted by influenza. So you see some outliers there because the influenza severity varies a lot from year to year. I think it was, they just announced it was 80K in 2018, I think. Yeah, it was 2018, I think it was 80K, and it was like only like 27K, I think, in 2016, if I remember right. So it varies by a factor of 2 or 3 from year to year, and that's heavily loaded, of course, in the winter months. And then let's look at this now factor 2 scores. So how do the factor 2 scores trend over time? So the factor 2 scores were flat for a while, and then after 2013, they started going negative for females, and actually basically the same for males. So let's remind ourselves, what does it mean for the factor 2 scores to go very negative? It means that you're getting this flattening effect. The composition of mortality is flattening out. Relatively fewer older people are dying, relatively more younger people are dying. Of course, absolutely more older people are dying than younger people, but relatively the trend is in that direction. So that's unfortunately not something we'd probably want to see, but it is what we're seeing is that the mortality is the overall mortality in the U.S. is still basically going down, except for that one reversal I pointed out earlier around 2016 to 17 for men, probably due to opioid abuse. But so the overall mortality is going down, but it's troubling, of course, that it's shifting its profile. I mean, in some sense, if you've got to have a certain level of mortality, you would rather it be concentrated among older people. And in some sense, it's flattening out. That probably isn't a good thing. Now, I'm not a not really qualified to make too much of a statement of that sort. That's just my sort of layman's takeaway from that. But again, I think the main thing here is you can learn something from this PCA analysis that's complementary to what we learned from the GLM analysis. And of course, there's many other things that one could do with these data. A lot of people really love multi-level models, so generalized linear mixed Poisson regression would be a very useful tool to bring to bear on these data as well. Of course, I didn't do that today. I kind of prefer to avoid that technique unless I absolutely have to, but it's a great technique. I mean, when you use it, it's great to use. But it's like the 200-pound gorilla, a big, complicated tool that the algorithm can take forever to fit and so on. So I'm basically focusing on things that are a bit lighter weight than that, and showing that we can still learn a lot from the data. So of course, the connection to COVID, just to kind of wrap up with that, is that we would be very interested in understanding. People are doing already excess mortality analyses to try to get at. There's all kinds of concerns about the reporting of COVID deaths. They may be overreported in some ways, they may be underreported in other ways. If you just go to all-cause mortality, you don't have to worry about vagaries about the cause of death. And there are a lot of interesting work I'm sure will be done over the next few years about understanding how the COVID effect superimposes on this. There's this notion of life years lost too. When the death of a 40-year-old leads to many more life years lost than the death of an 80-year-old. And so understanding the structure of mortality pre-COVID and then superimposing COVID on top of it will lead to a lot of insight about exactly what the burden of the COVID is in many different ways of looking at it. And so I'm hoping that there'll be a lot of thoughtful statistical insights brought to bear on those analyses as they start to get off the ground. But for me, at least with the data I have access to, I can't really participate in that yet. But hopefully some of these earlier versions of some of this data might come out sooner than they otherwise would, hopefully, so that people can start looking at these questions more carefully. Okay, so that's about all I have. Maybe we can now, I'll stop sharing this, and James, if you're still there, can you unmute everyone? And
yeah, I'll see what I can do. So the way that Zoom webinar works is for, if anyone wants to chat, well, let's see.
I mean, people have been chatting already.
Yeah,
so
if you can give me a quick second, I'll allow everyone to talk.
That's fine. And feel free to also
whoever's willing to can,
chat.
You can unmute you should be able to unmute yourselves. If you can't, just let me know.
Okay.
In the chat window, and I can unmute you all as well.
You can ask questions about the analysis. You can just ask practical questions about how to run this on your machine. What does the code mean? We could get into the code now if people want to get into the code. We could just end now. That's totally fine. I'm losing my voice. Also, questions, comments about possible future topics would be welcome. Things you'd like to learn. Any suggestions about formats is always welcome as well. 2 hours is about how much I can have the stamina for. I think it's what most people have the mental energy for. If anyone has trouble running this code, let me know. I ran it on my very standard Python install and it worked fine, but Python's usually pretty stable across different versions, but if you have trouble running the code, if you get unexplained errors, you can email me offline and I will try to resolve them. Okay, last call for questions. If not, thanks everyone for attending, and we haven't actually scheduled the next one of these yet. This is going to be more like a sporadic series rather than like a very, very regular series. Oh, good. James, do you have an answer to that question?
Yeah, the recording will get posted. It usually takes a couple of days for Zoom to fully process it, and then we'll get it shared, and we'll probably post it both on Midas's site as well as CSCAR's.
That's great. I'm not even sure we have a site to post it, but if we do.
Fair enough. Well, it'll at least be hosted on Midas's end.
It was at Midas, yeah. Okay, thanks, Daniel, for that comment too. All right, if anyone's doing research that involves these sort of things, we support all this stuff at CSCAR, so you can make an appointment to come in and talk to us at CSCAR. Okay, that said, we'll wrap up, and we'll try to get the next one scheduled soon, and then it'll be 2 to 3 weeks down the line because I'll have to find time to put stuff together. I'll have to decide what it's going to be, but we'll get it scheduled, and before mid-June, let's see, probably early June, we'll have iteration 2 of this, and we'll kind of continue a pace throughout the summer. So thanks, everyone. Take care. Good evening.
Awesome. Thanks so much, Kirby.
Sure.